Hi everyone, in this video I'm going to discuss how we actually discretize our system for this diffusivity inverse problem. So I'm going to cover a lot in this video, so I'll just very briefly cover a lot of this stuff. So our Lagrangian for our diffusivity problem, just to review, is given by this integral form. This is our data misfit, this is our regularization, and finally this is our PDE constrained weak form of our diffusivity model. And let's just take our domain to be a square in 2D. And so if you haven't seen finite element methods before, the reason why we're doing all this in weak form is A, because it's a nice framework, and B, finite element methods naturally lend themselves to weak form. And 3, if you want the strong form, you can get the strong form out and do finite differences if you want. So just as a brief, very brief overview of finite element methods, if this is our domain, 0, 1 cross 0, 1, then the finite element method, if we use triangular elements, it views each part of the domain as a subdomain, omega 1, omega 2, omega 3, omega 4, omega 5, omega 6, and so on. And it solves that weak form locally on each one of these, and then builds a matrix equation that gets the global system, and you solve that linear system. If we look at a specific triangle, we label the nodes x1, x2, x3 for each one of these omega i's with a counterclockwise orientation, and we choose basis functions phi j such that basically x1, the function is going to be 1 at this value, and it's going to be 0 at all the others. So this is a Kronecker delta jk. So just to illustrate this, if this is omega 1 and omega 2 across these two triangles, so this is omega 1 and this is omega 2 in red, then for example, this green, or let's start with the yellow. So this is phi 1, 1, so this is x11 right here is equal to x3, 2, where 2 tells me the subdomain I'm in, that's the I. This basis function is 1 at x11 and it's 0 at the other points. So it linearly decays. It has to be a continuous function in this context for continuous Galerkin, and it just decays down to 0 across each element. Phi 2, 2 says, okay, well, let's look at x22, which is back here in the red. I'm 1 here, and I decay down to 0 here. And then if treated globally as a function, it's 0 everywhere outside of that element, which is why I've drawn, sort of shaded this. All 3 of these are all 0 outside this element. And then finally, phi 1, 2 follows a similar trajectory. So again, this is a very, very brief overview of finite element methods. If you want more details on this, a good reference is it's either the finite element method or finite element methods by Tom Hughes. This is a great textbook on this topic, and there's various online sources you can look at too. So at the end of the day, the whole point of finite element methods is I can map any continuous field alpha to alpha h, where h is just saying, okay, this is a discretized version of what we're talking about, still viewed as a continuous field. It's the sum of some coefficients alpha, alpha n, times the basis function phi n, where now I've gotten rid of all these superscripts. Viewing each one of them, I could relabel. I have 3 basis functions for each one of these. I could label them globally without this I here. And again, this reference here, finite element method by, or the finite element method by Tom Hughes, talks about this. So there's an array that basically maps. There's a matrix, essentially a function that lets you take these indices here into just some global index, because this is much simpler, right? I don't have to worry about the elements per se. And so I just relabel. So that's just the basis of finite element methods so that we know what we're talking about. So there's 6 steps that we're going to follow. We're going to start with the forward solve. And this is what our weak form looks like for our diffusivity problem. And again, this is a Galerkin method. And the Galerkin, it just refers to this discretization way of doing it. And our goal is to find some discretized version UH that's in the span of these basis functions, such that for every discretized test function p hat, this is what we're varying, that's also in the span of these basis, in this basis, then such that this is equal to, sorry, I lost this color, so this is equal to 0 for each one of them. So basically, everywhere we replace this UH with UN phi n for n unknowns. And the trick here is that p hat varies over all of them. And each one of these phi's are linearly independent. So we can get a matrix equation of this form. We sum over, again, this is a constant, so it comes out of the integral. And we can evaluate these integrals because we know the form of these phi n's. So at the end of the day, this equation can be written as kmn un, sum over all of them, equals fm. And this looks like a matrix equation where each one of these are just, these are values now, right? Because I can evaluate those integrals. So this is a matrix equation of the form ku equals f, where k is in Rn by n, f is in Rn, and u is in Rn. Okay, yes, and then from here you just have to take care of the boundary conditions here. So again, let's just assume for simplicity that the first j basis functions are equal to 1 on the boundary of omega, and we have a 0 Dirichlet boundary condition. And so you basically just reduce your matrix equation into this sort of form here at the bottom. And that's pretty much all there is to it. You're gonna solve a linear system for your unknowns, knowing that at the end of the day, that vector really represents a linear combination of the basis functions of interest. So very similarly, this is our adjoint equation. We discretize by now taking pH to be in the span of these functions and UH hat to be in the span of our basis functions. Solve this, set this up. Now U hat is what we're varying. So we set this to be some basis function, because we know it has to be satisfied for each U hat H, and our basis functions are linearly independent. And then finally, we can build this, and then again, we take care of boundary conditions, just like before, to get this final system, and then we solve for P tilde here. And finally, for the gradient, again, this is our weak form in this particular case of the diffusivity problem. We discretize it like this, and now we just evaluate it. We're not solving for anything. So just to show you all the nuts and bolts here, if you know what m is, you don't even necessarily have to write it in, well, you do have to project it into this basis typically. So the point is, given an m hat, given any m hat, I can compute this this operation, which is the gradient inner product, and so it's of this form. These are just numbers, right? So I can put this in a matrix. There should be a phi n or a phi k in here. So then this right here, so gradient UH and gradient pH are now known. There should be a phi k in here. And so this gives some vector b that I'm dotting that into. And so I now have something of the form of vector dotted into another vector and a vector dotted into another vector. So you can view this as just, well, okay, that's just this vector, right? And so you can get the gradient in vector form this way. And then gradient descent, you're just going to take, now you have this gradient, and then you have a descent direction if you're doing direct gradient descent here. And you do backtracking line search just like before, because this is now in vectorized form. You update this m, and then because all of this depends on m, you keep iterating through gradient descent. Now, if you want to go through Hessian action, you solve the tangent linear model or the incremental forward problem, and this is what it'll look like. Again, you discretize just like before. Similar for the adjoint problem, you discretize, you solve for this p tilde. So this is our Lagrange multiplier u tilde. Solve for that in discretized form. Solve for p tilde in discretized form. And similar here, we compute the Hessian action. This is slightly different from the gradient. At this point, m, p, p tilde, u, and u tilde are knowns. M tilde is what we're ultimately trying to solve for, because this is going to be our search direction in the context of Newton's method, if we're using Newton's method instead of gradient descent. So we want to solve this system. The Hessian acting in our search direction m tilde is equal to minus gradient. That is, again, similar to before, that's if and only if. For every m hat h, dotting that into this vector is equal to m hat dotting into the gradient, the minus the gradient, which is true if and only if for every basis function, en, right, because we're in discretized form here, that dotting that into the Hessian action, the Hessian, actually the m tilde direction is equal to that in the minus gradient direction. So what that tells us is that we can form this as a vector as taking this integral form, right? So this is defined as h of m. So we evaluate this at m, and then we view it as, if you give me a direction m tilde that I'm perturbed, so this is the direction I'm taking the gradient in, and this is the perturbation. So it takes two parameters, basically. We can evaluate this as via this integral, and the way we form that is simply taking this, if you give me a search direction m tilde, I evaluate m hat to be phi 1 through phi n. That gives me a vector. And then finally, we just solve this system. We know how to get a vector out of this left-hand side. We formed this right-hand side before we even got here. And we just give it some initial guess, m naught h, and we just plug it into Newton-Krylov. So we use an iterative solver here, some Krylov subspace method, and we terminate the solve early if on step k, step n, I used n here, step n of our linear solve, we solve we terminate early if the norm of the residual, so this is the residual because the plus is because the minus gradient here, so minus minus, is less than or equal to some eta times the norm of the gradient here, where again, if we want to see superlinear convergence, but still be more stable than Newton's method, I sort of quote unquote a vanilla, Newton's method, we take this to be to go as the norm of the gradient to the 1/2 power, because then we get sort of this 3/2 power convergence. We get the superlinear convergence. But when we're far away, we still descend like gradient descent, so we're a little bit more robust as well. So this is a lot of information to unpack. So I wanted to keep this as brief as possible. So go back and review this if this is a bit too fast, and we'll in the next video I'll show you guys a different example of an inverse problem, or I'll show you. I'll either show you this framework for a different seismic problem, or I'll actually show you some numerical examples. I'm not sure what I'll do yet, but thank you guys for watching. And again, review this a little bit more if this was a bit too fast. It's a lot to take in. All right, thanks.